All right, so vectors. So a vector, it is a quantity that has both a magnitude and a direction. Okay, so it has a magnitude and a direction. Well, what's magnitude? Magnitude is the length of the vector. Okay, so over here, this diagram, that would be the length. So you'd have to figure out the length. You could figure out the length of a vector by doing something like the distance formula. That would be the magnitude. Direction is the angle that's formed with the x-axis. And it's always our x-axis going off to the right here. So we would need to figure out what that angle measurement is, and we would be able to do that using sine, cosine, or tangent to find the angle measurement. Okay, so a vector has both magnitude and direction. If you ever see anything that says standard position just means that our initial point is at the origin, so we are starting at 0, 0, and the vector is pointing off in some other way. And then component form is an ordered pair that represents the vector. And if you have 2 points, so normally we have 2 points, like here we have a point for A and a point for B. So, I don't think I want to write in highlighter. So let's say we have 2 points, and our 2 points are x1, y1, and x2, y2. The way how you do component form is you use these square, like Pac-Man brackets, and you subtract your x's. So you do x2 minus x1, and then you subtract your y's, y2 minus y1. So the change of x and the change of y, yeah. And then that's your vector. That'd be your form, your component form. So what we're going to do today is we're going to write component forms for vectors, and then we might do a little bit of transforming them too. We'll find magnitude and direction tomorrow. So first off, the notation for a vector is that it's a ray with just the one little arrow thing up. Okay. So anytime you see this notion, it means that we are talking about a vector. So first 2 examples from these graphs, we want to write the component form. So the thing here, what we have to do is we always want to make sure that we are starting with the first value. So if we want to go from E to F, we have to start with E and go to F for the vector. So here, when I do my change of x's, I have to start with my value at E and go to my value at F. So I would have to do 1 minus 7 here for my x's. So to do component form, I would do 1 minus 7 for my x's, and then my y's would be 5 minus 4. Well, what's 1 minus 7? Negative 6. So this would be negative 6, and 5 minus 4 is 1. So this component form for this vector EF is negative 6, 1. Okay? All right, let's do the same thing for number 2. We want to write the component form for vector AB. So which point am I going to start at? A. So here's A. So I would take, for my x values, I would take negative 4. Yeah, minus the negative 5, which would be plus 5. So, oh, sorry, negative 1. I don't know. Negative 1. I was looking backwards. So that'd be 4. And then for the y's, what would we have to do?
Negative 4 plus 1.
Negative 4 minus negative 1, which would end up being a negative 3. So that vector is 4, negative 3. I also want to point out one other thing about this on the graphs to you. And that is here, if we look at where we ended at, and went to where we started at, so if we look at F and if we count backwards to E, we had to go left 6 and up 1. Left 6 and up 1. Okay? If we look the same thing here for A to B, if we start at B, we had to go to the right 4, and then down 3. So that is another way that you can take a look at it. But it really is just subtracting them. So is that okay? Okay. Equal vectors and parallel vectors, I just want you to know what they are. We're not going to do too much with them. But an equal vector, they're equal if they have the same magnitude and direction. So they have to be the same exact length, and they have to be pointing in the same exact way. Okay? If they point in different ways, then they're not the same. Parallel vectors, they have to have the same or opposite direction. So those two would be parallel because they would have the opposite direction as one another. But they're not equal, but that's okay, so they could be just parallel. So these would be parallel, but not equal. So for you to be equal, I'll put congruent marks on there so we know for sure. These are the same length, and they're pointing in the same direction. So these two we would consider equal to one another. Okay? They don't have to be right on top of each other. They just have to be pointing in the same way and having the same length. So what we're going to do is we are going to translate the image of triangle ABC with the vertices. A is at -3, -1. B is at -1, -2. C is at -3, -3. And we want to translate this under the translation of the vector 4, 3. Well, what do you think? Okay, so we'll start by plotting the points. Good call. So here we have A is at -3, -1. B is at -1, -2. And C is at -3, -3. That little guy right there. Now the vector, this is written in component form. So the component form here, this told us, the first value told us what? The change in what? The first value told us the change in x, right? So your change in x is a +4. And your second value tells us the change in y is a +3. So for each of these, what are we going to do? Yeah, we're going to go to the right 4, and then we're going to go up 3. So 1, 2, 3, 4, 1, 2, 3. Okay, do that for each point. So there's my new A prime, B prime, 1, 2, 3, 4, 1, 2, 3. Ooh, I went something wrong. Put B at the wrong spot. I missed the point. There you go, and then C, 1, 2, 3, 4, 1, 2, 3. So it should look the same, it's just moved to a different spot. Is that okay? Yeah? It is a lot like translation, except for translation here we would have said x plus 4 and y plus 3. So here we just have to know that when we have that notation, that's what we're doing. Okay, there's one other thing that we're going to do with this, and that is we're going to talk about the resultant, and then we're going to translate using the resultant. So the resultant is when two vectors are added together. So you just take two vectors, you just add their corresponding parts together, you have something called a resultant. Okay? So here we want to translate the image of R as QT with those vertices. Q is at -4, 4. R is at -1, 4. S is at -2, 2. And T is at -5, 2. Under the translation of M, which is 5, -1, and N, which is -2, -6. So how do you think we could do this? Okay, well first, plot the points. So let's plot Q, R, S, and T. So Q, -4, +4. R, -1, +1, or +4. S, -2, 2, and T, -5, 2. The pen's jumping all over. Okay, there's my quadrilateral. Now how will I graph my new image?
Could you just like go to QR and make that vector M?
We wouldn't make that vector, and we want to translate it underneath these two vectors. We were not going to subtract it. We could do this two ways. We could first translate it underneath M by adding 5 to all of your x's and subtracting 1 to your y's. And then translate it underneath N by adding a -2 to all your x's and adding a -6 to your y's. Or you could find the resultant of M and N. And then just translate it underneath that.
So 5 minus 2.
Yep, so 5 plus -2 and -1 plus -6. So this would be 3 and -7. So now instead we could find the resultant vector and move it this way. Instead of doing it in 2 separate steps, we could do it in 1. So 3 tells us, what are we going to do with the 3? Yep, 3 to the right, and then the 7 down.
So if you didn't do it with the resultant, how would you do it?
You would first do the M, so you'd go 5 right and 1 down. And then you do the N, 2 left and 6 down.
So you move it like twice.
You'd move it twice, yeah. And you'd get to the same ending position, but... So for each of these, take it 3 right and 7 down. 1, 2, 3 right. 7 down. 3 right, 7 down. 3 right, 7 down, and plot your new one. Is that okay? All right, that's all we're going to do today, because we're going